You know that feeling, that moment of surprise, maybe even a little bit of betrayal, when a tool you just trust, something you rely on every day, suddenly does something, well, wrong.
Yeah, it's unsettling, especially in tech, right? We build so much on trust. Trust in libraries, trust in platforms, trust in our developer tools.
Exactly. And what happens when that trust gets, broken? That's what we're diving into today, a really recent incident that shakes that foundation a bit.
It's a fascinating case study, honestly. It really shines a light on just how interconnected everything is. A weak link somewhere small.
Can cause big problems elsewhere.
Precisely. It can send shockwaves through the whole software ecosystem. We spend so much time thinking about our code's security.
But maybe not enough about the security of everything our code depends on.
That's the crux of it.
Okay, so today we're doing a deep dive into the recent compromise of two really widely used GitHub actions. First, there's TJ Actions Changed Files, that's CVE 2025-30066.
And the sort of precursor to that, review dog action setup, which is CVE 2025-30154.
Right. Now, for anyone maybe less familiar, GitHub Actions are like automated helpers for software projects. They handle stuff like testing, deploying code.
All those repetitive but critical tasks in the background makes development faster, more consistent.
Which is why their security is just so vital. They're plugged right into the heart of the development process.
They really are. They're core parts of the CI/CD pipeline. That's continuous integration, continuous delivery. It's how modern software gets built and shipped.
So a weakness there
Can have really broad, really significant consequences, yeah.
So our mission today, our goal for this deep dive, is threefold. First, understand how this attack actually happened, step by step.
Second, try to grasp the potential impact. We're talking an estimated 23,000 organizations potentially affected. That's a huge number.
It really is. Think about the sensitive data exposure that represents. And third, most importantly, figure out what you listening and learn from this to protect your own projects, your own workflows.
We'll be leaning on some great research here, primarily from security folks at Step Security and GitGuardian. They did a lot of the legwork uncovering this.
Definitely. So the big question is, how could tools that seem so harmless, so widely used, become attack vectors?
Well, as we'll see, it wasn't straightforward. It involved a chain of compromises, exploiting trust, exploiting dependencies. It's a supply chain thing, really.
Okay, let's unpack this then. You said it was a chain reaction, not just one event.
Exactly. It didn't start with the biggest target. It began with review dog action setup. Seems like that was compromised around March 11th, 2025.
And how did they get in there?
The most likely vector seems to be a compromised personal access token, a PP.
Like a password or key.
Sort of, yeah. A token belonging to one of the maintainers of the review dog action, which just highlights, how crucial securing every access point is, even personal tokens.
And was this easy to spot?
Apparently not, initially. And here's a key detail. For organizations on the free tier of GitHub, changes made to Git tags, they aren't audited by default.
Oh, so they could change things without setting off alarms.
It gave them a window, yeah. A way to operate stealthily, at least for a bit.
Right, like slipping in through an unguarded door.
Wow.
And this leads to that concept you mentioned, island hopping.
Exactly. It's a classic tactic. Don't go for the main fortress right away. Compromise something smaller, maybe less scrutinized.
Like review dog in this case.
And use that as a stepping stone to get to something bigger, more widely used, like TJ Actions.
Which relies on review dog.
Not directly TJ Actions changed files, but another action in the TJ Actions family did. It shows how dependencies create these pathways.
So compromising one seemingly minor thing can have these downstream effects.
Absolutely. It's a hallmark of sophisticated supply chain attacks. You need vigilance across all dependencies, not just the big names.
Okay, so how did the review dog compromise then lead to TJ Actions getting breached?
Yeah.
You mentioned a dependency.
Yeah. So there's another action called TJ Actions lint changed files. That action used review dog action setup as a dependency.
Ah, okay. So the malicious code hidden in review dog
Got pulled into the ESLint actions workflow when it ran. And crucially, it ran with the permissions that the ESLint action had.
and those permissions were enough.
Apparently, yes. Enough to let the attacker steal another PAT. This one belonged to the add TJ Actions bot account.
And that bot had permissions?
It had write access to the main TJ Actions changed files repository itself.
Wow. So one compromised key unlocked a path to a much bigger vault.
Pretty much. It's a perfect illustration of that cascading impact. Trust in one component implicitly extended to its dependencies, creating the attack path.
Okay, so then came the direct hit on TJ Action's changed files. When was that spotted?
That was detected around March 14th, 2025 by Step Security. The attackers used that stolen bot token, the @TJ Actions bot 1,
To push bad code.
to push a malicious commit straight into the TJ Actions changed files repository.
But here's the really clever or scary part, right? The tags.
Oh, yeah. This is what made it so insidious. They didn't just create a new suspicious version. They went back and changed all the existing version tags.
All of them, like V1, V2.
Everything. From V1 all the way up to the latest V45.0.7. They made all those tags point to their single malicious commit. The commit ID was 0A58D.
Hang on. So, even if you thought you were being safe using an older stable version tag,
You were actually pulling down their malicious code because the tag itself had been moved.
that completely breaks the trust in versioning, doesn't it? I always assumed a tag like V1 was fixed, immutable.
You'd hope so, and usually that's the expectation, but tags can be moved, unlike commit hashes. This attack really weaponized that fact. It shattered that assumption for these actions.
Okay, so what was this malicious code actually doing once it got pulled in?
Two main things, it seems. First, the most straightforward. It tried to print any secrets it could find, API keys, passwords, tokens, directly into the build logs.
Just dump them out in plain text.
Well, sometimes maybe encoded, but yeah, into the logs where they could potentially be seen. But it didn't stop there. It also did something sneakier.
Which was?
It included instructions hidden using double base 64 encoding to try and avoid detection.
Double base 64. Why?
This makes it harder for simple text scanners to see what's going on, a common obfuscation trick.
Okay, so hidden instructions to do what?
To download and run a Python script called memdump.py.
Dump. That sounds bad.
It is. Its purpose was to scan the memory of the GitHub runner, the machine actually running the action,
Why scan the memory?
to find even more credentials. Things that might not be set as environment variables, but are just, floating around in memory during the process. A much deeper search for secrets.
Wow. Okay, that's thorough. So how long was this malicious version active?
Thankfully, the window for the direct TJ action change files compromise wasn't huge. It seems to have been from midnight UTC on March 12th to about noon UTC on March 15th, 2025.
And GitHub stepped in.
Yeah, their response was pretty quick. On March 15th, they temporarily disabled the repository.
Took it offline.
And then later that same day, they brought it back online after cleaning it up, removing the malicious code, locking out the attackers.
Okay. But there was another angle to this, wasn't there? Something involving Coinbase.
Yes. And interestingly, this happened before the big widespread compromise became public knowledge.
A targeted attack.
It looks like it. The reconnaissance, the planning seems to have started way back, maybe even November 2024.
Really? That far back?
Seems so. And then specific preparations targeting Coinbase were seen around March 12th, 2025, right before the main event.
What kind of preparations?
We saw some suspicious user accounts start forking Coinbase repositories on GitHub. They seemed particularly interested in one called Coinbase Agent Kit.
Like they were studying it, maybe?
Could be. And here's the key difference.
Yeah.
In the attack aimed at Coinbase, they didn't just rely on those manipulated tags we talked about.
No. What do they do?
They used a specific malicious commit SHA of TJ Actions changed files in the Coinbase workflows.
So not just hoping Coinbase used a bad tag, but specifically injecting a known bad version using its unique ID.
Exactly. It points to a much more tailored, precise attack, not just opportunistic.
Did it work? Did Coinbase get hit hard?
Well, reports indicate that credentials were leaked during this targeted phase, but Coinbase stated that no actual damage resulted.
So maybe their internal defenses caught it. Or the leaked creds weren't useful.
Possibly. Could be their monitoring or incident response kicked in quickly, but the attempt was definitely made.
So this targeted attack just before the main compromise. Feels like maybe a test run. Or perhaps Coinbase was the primary goal all along.
It's hard to say for sure, but it definitely seems plausible. Either a test or the main objective before they decided to cast a wider net.
It certainly shows that high-profile organizations might face these more directed, sophisticated attacks targeting their specific supply chain.
Definitely. They need to be extra vigilant about their dependencies.
Okay, so we understand the how. Let's talk about the what. What was the actual impact here? You mentioned 23,000 repositories potentially affected.
Yeah, over 23,000 using the vulnerable action. That's a massive potential footprint.
And GitGuardian dug into this.
They did. They analyzed about 14,000 of those repos and found something pretty stark. 70%.
Yeah.
70% were vulnerable simply because they were using those mutable tags, the floating tags like V1, V40, etc.
Wow. So the common practice of using simple version tags made them susceptible.
Hugely amplified the impact, yeah. If everyone had been pinning to specific commit SHAs, the tag manipulation wouldn't have worked like that.
And the risk level depended on the repo type,
Right.
public versus private.
Exactly. For public repositories, those build logs where secrets were being printed.
You were just out there,
Yeah.
publicly accessible.
Unfortunately, yes. Anyone could potentially browse those logs and find exposed credentials.
Ouch. And for private repos.
The risk was more contained, primarily to people who already had access to the repository and its logs, collaborators, team members. But crucially,
Yes.
if any of those exposed secrets were persistent, long-lived credentials, the risk extended way beyond just who could see the logs at that moment.
Right. Someone could grab an AWS key and use it weeks later.
Precisely.
So what kinds of secrets are we talking about? What was actually exposed?
It was a worrying list. GitHub tokens, obviously, including the automatic GitHub tokens, but also personal access tokens, PATs.
Okay.
Then cloud keys, like AWS keys, Docker Hub credentials, Jira tokens, even things like cloud.gov credentials, NPM tokens for package management,
Wow.
and even in some cases, private RSA keys. That's a pretty broad spectrum of sensitive data.
Definitely. But you mentioned a distinction between short-lived and long-lived secrets.
Yes, and that's really important for understanding the actual immediate versus long-term risk. GitGuardian found 603 distinct secrets leaked in their analysis.
Right.
But a big chunk of those, 77%, were those temporary ephemeral GitHub tokens that expire relatively quickly.
So thankfully, most were short-lived. That limits the damage window, at least for those specific tokens.
It does, but it still leaves nearly a quarter of the findings as potentially persistent credentials. PADs, AWS keys, those are the ones that pose a longer-term threat if not revoked.
Did GitGuardian check if they were still valid later on?
They did test them, and they found that only about 1% of all the leaked secrets they identified were still valid at the time they performed their checks.
Okay, so 1%, that's still potentially serious for those affected, but maybe suggests good rotation practices, or maybe the attackers grab them quickly.
Could be a mix of factors. Prompt rotation by vigilant teams, tokens expiring naturally, maybe attackers already used and discarded some. But yeah, the persistent ones were the main long-term worry. An AWS key leak could grant access for a long time if not caught.
And even with the short-lived ones, printing them to public logs is still bad, right? Easy pickings for anyone watching.
Absolutely. Attackers might target logs specifically because it's an easy way to grab credentials, even temporary ones, if they act fast, or just for reconnaissance.
This whole thing,
Yeah.
it really makes you question the overall security of the software supply chain and these CI/CD platforms we rely on.
It does. It definitely exposed what you might call a preparedness gap in a lot of places.
How so?
Well, organizations might have solid security for their own code, code they write internally, but maybe less scrutiny on the third-party actions, the dependencies, the automation tools they pull in.
Right. The focus is inward, not always outward on the things you depend on.
That seems to be a common pattern, yeah.
Okay, so let's shift to advice. If someone listening thinks they might have been hit back in March, what were the immediate, crucial remediation steps?
First things first. Identification. Did you use TJ Actions changed files between March 12th and 15th? Or reviewed org action setup around March 11th in any workflow?
Got it. Check usage during those specific windows. Then what?
Then the painful part. Log inspection. You had to meticulously check all the build logs from that period.
Looking for any dumped secrets.
Exactly. And remembering that double base 64 encoding trick, you couldn't just search for plain text keys. You had to look for suspicious encoded blobs, too.
Okay, log checks. What next? Assume the worst.
Pretty much. Rotate all potentially compromised secrets, even if you didn't see anything in the logs, if a vulnerable action ran a workflow.
Any secret that workflow had access to should be considered compromised and rotated.
Absolutely essential. Better safe than sorry.
And obviously, update the action itself.
Yes. Update to a known safe version or switch to an alternative. GitHub and Step Security provided specific recommendations, including Step Security changed files as a safer alternative.
What about those public repo logs?
Critical step for them. Review and delete any logs from the affected period that might contain exposed secrets. Those logs were the leak path.
And finally,
A deeper investigation. Look for any signs of further malicious activity. Did the attackers use any leaked credentials? Did they pivot elsewhere in your systems?
Okay, so those were the immediate firefighting steps. But
Right.
this shouldn't happen again. Let's talk long-term prevention, best practices.
Right. How do we build more resilient workflows?
And you mentioned one thing repeatedly, pinning actions.
Absolutely numero uno. Pin your actions to their full-length commit SHAs, not tags like V1 or at main. Use the full 40-character hash.
And why is that so critical? Again, explain it simply.
Because a commit SHA is like a permanent, unchangeable fingerprint for a specific version of the code. An attacker cannot move a SHA to point to their malicious code like they can with a tag.
Ah, okay. Tags are labels that can be moved. SHAs are fixed addresses.
Exactly. Pinning to a SHA guarantees you are always running the exact code you intended, completely blocking that tag manipulation vector.
Got it. Lock it down with the SHA. What's next?
Least privilege for the GitHub token. This is huge.
The token the workflow runs with.
Yeah. By default, it often gets broad permissions, like write access to your whole repo. That's usually way more than it needs.
So restrict it.
Definitely. Define the minimum permissions each specific job needs. If a job only needs to read issues, don't give it permission to write code. It's like giving a contractor a key just for the room they're working in, not the whole building.
Makes sense. Limit the blast radius if that token ever gets compromised. What about avoiding secrets altogether?
That's the ideal, where possible. And OpenID Connect, or OIDC, is the way forward here.
OIDC, how does that help?
It lets your GitHub Actions workflows talk directly to your cloud provider, like AWS or Azure or Google Cloud.
And get credentials automatically.
Exactly. But they get short-lived, temporary credentials just for that specific job run. No need to store long-lived keys or secrets directly in GitHub settings.
So instead of storing a permanent master key in GitHub, the workflow asks for a temporary key from, say, AWS each time it runs.
Precisely. It dramatically reduces the risk associated with storing static secrets.
That sounds much better. But sometimes you still need secrets, right? How should we manage those better?
Absolutely. Robust secret management is still vital. Few key things. Avoid putting structured data like JSON inside a secret, if you can help it. It makes automatic redaction and logs harder.
Okay.
Make sure you actually register all the secrets you use within GitHub. This helps GitHub know what to look for and redact from logs if it accidentally leaks.
Good point. Tell GitHub what your secrets look like.
And then basic hygiene. Regular audits, regular rotation of all secrets, maybe even mandatory reviews for any changes involving secrets or access to them.
What about just being pickier about the third-party actions we use in the first place?
Yes. Governance around third-party actions is key. Have a policy. Maybe an allow list of vetted, approved actions your organization trusts.
Review them.
For critical actions, absolutely. Review the source code. Or even consider forking the action and maintaining it internally so you have full control.
That gives you more control, but also maintenance overhead.
It's a trade-off, yeah. But for critical workflows, it might be worth it. Also, use tools like Dependabot to automatically get updates and security patches for your actions.
And they're tools to assess action security.
Yes, things like OpenSSF scorecards. They can give you an automated security health check on open source components, including actions. Very useful.
Okay, so vetting the actions themselves. What about securing the workflows that use them? The YAML files.
Critical point. Use code owners for your workflow files. This means specific people must approve any changes to those workflows.
Add a review gate.
Exactly. Use branch protection rules on your main branches. Make sure sensitive workflows only run on trusted code, not just any pull request.
What about actions creating PRs or approving things?
Be very careful there. Avoid letting actions automatically create or approve pull requests without human oversight. That can be abused.
And workflows running from forks.
Generally, disable workflow runs triggered by pull requests from forked repositories, unless you have a very specific, secure reason to allow it. It's a common attack vector.
It feels like we also need security during the actual runtime of the workflow, not just configuring it securely.
Yes, runtime security and monitoring. Tools like Step Security's Harden Runner can help here. It watches for suspicious behavior during the workflow execution.
Like what?
Like unexpected network connections, accessing unusual files, running strange commands. It adds a layer of detection right when the code is running.
And general CI/CD monitoring.
Comprehensive monitoring, yeah. Looking for anomalies in your build processes.
What if teams use their own machines? Self-hosted runners.
That brings its own set of security considerations. Big one. Avoid using self-hosted runners for public repositories, if at all possible. The attack surface is just too large.
Okay, so keep them for private repos.
Preferably. And for private repos, make sure the underlying machine is secured properly. Use ephemeral runners where you can fresh machines for each job, then destroyed.
So nothing sensitive lingers.
Right. And minimize any sensitive data stored permanently on those runner machines.
And finally, just good old-fashioned auditing.
Can't forget the basics. Regularly scan your GitHub Actions logs for any accidental secret exposures. Use GitHub's own security and audit logs. They track changes to workflows, secrets, permissions. Monitor that activity.
It really paints a picture of needing multiple layers, doesn't it?
Yeah.
Defense in depth. No single silver bullet.
That's exactly it. This attack succeeded by exploiting weaknesses at several points. A layered defense combining pinning, least privilege, OIDC, good secret hygiene, vetting actions, runtime monitoring. That's the strong posture.
It also feels like this incident highlights the cost of maybe prioritizing convenience over security sometimes, like using easy tags instead of SHAs.
That's a great way to put it. It's like accumulating technical debt in security. Using mutable tags is easier, faster maybe, but you take on risk.
And eventually that debt comes due, often painfully.
Exactly. There's a real need to invest in making the secure practices the easy default path.
So wrapping up, what are the main takeaways here?
I think first, just the sophistication of modern supply chain attacks. They're real, they're complex. Second, the critical need to understand not just your direct dependencies, but the whole chain. Your dependencies.
And the tools you use to build things.
And the tools, absolutely. Third, proactive security in CI/CD is not optional anymore. It's essential. Pinning, least privilege, OIDC, monitoring.
And finally, maybe question implicit trust. Don't just assume a popular tool is secure. Verify.
Precisely. Replace implicit trust with proactive, continuous security measures.
So, a final thought for everyone listening. Take a hard look at your own workflows. How much third-party code are they running? Do you really know what's in there? Do you have the visibility, the controls to spot something like this if it happened to you?
What concrete steps can you take, maybe even today or this week, to start hardening that supply chain? Reviewing your actions, checking for pinning, looking at token permissions.
I mean, now's the time for that review.
Definitely. And if you want to dig deeper, check out SISA's Known Exploited Vulnerabilities catalog, the KEV list. See what's being actively targeted out there.
Good resource.
Research OpenID Connect more, see how you could use it. Explore tools like Step Security's Harden Runner, Open SSF scorecards. Get a baseline of your security posture.
Lots to think about, lots to explore.
It's an ongoing process.
Well, thanks for diving deep with us into this. It's a complex incident, but understanding these threats is really the first, most crucial step towards building a more secure development environment for everyone.